Okay, now geometry aside, we can prove that if V1 and V2 are linearly independent, then the set V1, V2 minus projection on V1 of V2, that is V1, V2 prime, is linearly independent and orthogonal. And I've got an extra letter in there. I don't know where that came from, but let's go ahead and smudge it out. Okay. I know where it came from. I wrote it. Okay. Now these vectors are linearly independent. That is, these two vectors are linearly independent if and only if C1 V1 plus C2 times V2 minus the projection is equal to 0. When C1 equals C2 equals 0, and only when C1 equals C2 equals 0. Now clearly if C1 and C2 are both 0, this is going to give you the 0 vector. But the question is, does this condition ensure that C1 and C2 are both 0? Well, let's write it out. Right here's our equation. So I write it out again. And now I do some simplification. I can distribute the multiplication by C2 through this term here. I get C2 V2 minus C2 times the projection of V2 on V1. So the equation becomes this. That's very straightforward. Now what can we do? Well, let's write out what the projection on V1 of V2 is. Remember, it's V1 dot V2 over magnitude of V1, the scalar projection, multiplied by V1 over magnitude of V1, the unit vector in the direction of V1. So we have this. And now we see that this projection is a multiple of V1. In this step, I go ahead and combine the magnitude of V1 and the magnitude of V1 here, get magnitude of V1 squared, and observe this is just a scalar, so this is just a multiple of V1. So now we can factor out the V1 from this term and this term. We get C1 from this one, and C2 times this V1 dot V2 over magnitude of V1 squared here, all times V1 plus C2 V2 equals the 0 vector. Now one temptation that you might have when you see this expression here is to try to factor V2 out of these two terms. Okay, we've talked a little bit about why you can't do that. If you try to factor V2 out of these two terms, you have a C2. That's perfectly okay. But then you have minus C2 times the projection on V1. Stop. Projection on V1 is not a scalar. Projection on V1 is an operator that operates on V2 and gives you a multiple of V1. And you might want to think about that. So you've got to be careful to apply the rules of algebra correctly. This would not be a like term with this. But when you do this, you now have a scalar in front of V1 and you can do the factoring. Okay, well, where does that get us? Okay, we want to establish that C1 and C2 both have to be 0. Well, let's rewrite this up here, same equation. So we use the fact that V1 and V2 are linearly independent. And if V1 and V2 are linearly independent, then the only way they can add up to the 0 vector, and that 0 vector ought to have an arrow over it, the only way they can add up to the 0 vector is for this to be 0 and this to be 0. Because what's a test for linearly independence? Linear combination is 0 if and only if the two coefficients are 0. So this means that C1 minus C2 times this dot product over this magnitude squared is 0, and C2 is 0. Okay, well, certainly C2 has to be 0. Okay, if C2 is 0, then we have C1 minus 0 here. Okay, which means that C1 minus C2 times this is just C1, and that has to be 0, so we've concluded that C1 has to be 0. So now we know that C1 equals C2 equals 0, and the set v1, v2 prime, or the vectors v1 and v2 prime, are linearly independent. They're also orthogonal. How do we prove that they're orthogonal? We take the dot product. v1 dot v2 prime, and maybe I'll write that out here, v1 dot v2 prime equals 0 with a question mark over it. Is it so that v1 dot v2 prime is 0? Well, we write out v1, we write out v2 prime, and we do the dot product. We get v1 dot v2, just distributing, the dot product distributes, and then we get v1 dot v2 over magnitude of v1 squared times v1 dot v1. Okay, but v1 dot v1 is just magnitude of v1 squared, and maybe I'll write that out explicitly. So that this term is the same as this. This is just magnitude of v1 squared divided by magnitude of v1 squared, and what are we left with? We're left with v1 dot v2 minus v1 dot v2. That's 0. So we've proven that these vectors are orthogonal. Now the Gram-Schmidt process goes on to higher dimensions, to greater number of vectors. If you had v1, v2, v3 all linearly independent, then v2 prime would be v1 minus the projection on v1 of v2, and then v3 prime. Okay, here we've thrown away the part of v2 that's in the direction of v1. To get v3 prime, we throw away the part of v3 that's in the direction of v1. We don't need it. So we subtract off the projection of v3 on v1. And then we also want this vector to be perpendicular to v2, or if you prefer to v2 prime. So we could subtract the projection on v2 of v3, or if we prefer, the projection onto v2 prime of v3. Doesn't matter whether you project onto v2 or v2 prime. You're throwing away the part of v3 that's in the direction of v2. And this leaves you orthogonal to both v1 and v2 prime. So the set v1, v2 prime, v3 prime is orthogonal, and as a bonus, the set v1 over magnitude of v1 v2 prime over the magnitude of v2 prime. My commas and my absolute value signs are kind of getting blurred here. And v3 prime over the magnitude of v3 prime. And this is orthonormal. And this is kind of a big deal. I've alluded to the fact that you have function spaces that span certain classes of functions. We haven't done much with that because we can't assume the level of calculus necessary at this point of the course. But there are many other applications where this is also important. So this is a big deal. Just make sure you understand this as well as possible. And of course, if we went to 4 linearly independent vectors, we would subtract off the parts of each vector that are orthogonal to the previous ones. And we would end up again with an orthogonal set, and we could easily normalize it.